Aromatic reactions. Oh my God, look at this. Half black, half blue. Talk about that. Okay. So aromatic reactions are a huge, huge chapter, this suggests. Okay. And aromatic reactions are also very, very different because you will remember this reaction that we wrote out. And you can draw rings if you want to in your benzene ring. Um, the the times that we draw the double bonds is when I'm trying to show you the mechanism, okay? Otherwise, you can draw rings. It's totally fine. And so we said that, okay, so if we treat this with bromine, we actually got no reaction for this, okay? So which means it doesn't do addition reactions. It does do, hold on. No, something happened just now to my computer, but I think it's fine. I don't know. It does do substitution reactions. So now if I take bromine and now then I use a catalyst, I will get substitution. So which means that I got rid of the hydrogen and have bromine there. So this is substitution. Now, first of all, what kind of substitution is this, right? Because we've done SN1, SN2 before, and both of those are substitution reactions, first order, second order. So what's going on here? And let me remind you, okay, of one thing that it was not a huge thing, but we did talk about this a little bit when we were talking about SN1, SN2 reactions. And I said to you that if you had a leaving group on the benzene ring and you treated it with a nucleophile, you will also not get any reaction because we cannot do this kind of a reaction because the nucleophile is electron rich, but so is the benzene ring. This is also electron rich, you know. So electron rich will not attack electron rich. I'm going to break some of my own rules, okay? You're sticking around long enough to figure out that you can break rules, you know, and we will break rules, okay? So we learn something, but then, you know, as time goes on, we learn something more. So generally, like, you know, in organic one, we learned that you cannot do SN2 reactions on benzene rings. Besides, if you look at the reaction that I have with bromine over here, the leaving group is hydrogen, right? Hydrogen, come on, you know, like hydride is not even a good leaving group. You know that that's the worst kind of leaving group possible. So, which means that this reaction is really quite a different kind of reaction, you know, this kind of substitution. So what happens in this case with the benzene rings, okay, is that the benzene ring itself is the nucleophile. So benzene ring is nucleophile, okay, in these cases. So which means that the bromine then is the electrophile, which means these are going to be called electrophilic substitutions. In the nucleophilic substitutions, we were writing the nucleophile on the arrow. We were, you know, attacking with the nucleophile. That's kind of how it was going. Here, we're going to be writing the electrophile on the arrow, and the nucleophile is the benzene. That's going to be doing the attacking because that has the electrons. So now things are a little bit switched, okay? So these are called electrophilic substitutions. Okay, fine. I can handle that. But let's talk about the mechanism then, okay? How does it work? I'm going to write a generic mechanism for you because all the reactions are going to work exactly the same way. Okay, so here you have an electrophile. And if, you know, if you're writing this, then draw the double bonds out. I didn't say this before, but I'm going to say this now, that please, when you're drawing your benzene rings, make them nice. You know, you must have heard of that joke that a lot of organic chemistry students say that, you know, I took organic chemistry and all I learned was how to draw a hexagon. You know, it's a very common joke, but yeah, please draw that hexagon nicely. Okay. And so make sure that it's nice and symmetrical. Make sure your double bonds are nice. If you're drawing the ring, then make sure your ring is actually not like this in a small manner. It should be a nice big size ring, you know. So make it a nice looking structure, okay? All right. So here's the electrophile. And then now the double bond is going to attack the electrophile. Remember, each carbon has a hydrogen. Draw it out if you need to, okay? Because sometimes we forget that there is a hydrogen there. So draw that out. So you have this now. Now the double bond is the one doing the attacking, which means that you still have the hydrogen here, you have the electrophile here, and the second carbon is going to have the hydrogen and also the carbocation. This is not a normal carbocation, okay? This is not the kind of carbocation that we generated in organic 1, okay, or with alcohols. This is not the same thing because this is part of an aromatic structure, okay? So now what happens with this carbocation that we have, we are going to start getting resonance, okay, in this one. So I don't know if I want to change colors anymore. It's just too time consuming. So I hope you will see this. So here is the electrophile, here's the hydrogen. And if you don't want to draw the hydrogen, you don't have to, but remember it's there, okay? And so there is that. Now the positive comes here. Then here is the other resonance structure. Let me do this, that, the double bond here, and then the positive is here. So which means that it's a nice resonance stabilized structure, okay? Which means that this reaction, this intermediate is quite stable, which means that the reaction is going to go forward, okay? You can write the hybrid. So the hybrid equivalent to this is the hybrid. Here is the electrophile. And then you write like a C, okay? Because the aromaticity is broken. And then you draw plus inside there, okay? So it's not a full aromatic structure. You still have the hydrogens here and here. The other carbons also have hydrogens since the reaction is not taking place there. So then the last step is where the conjugate base will come in and pick up the hydrogen from here. And this will drop its electrons back into the ring. And all is well in benzene world. You can see how important resonance was, and why Klein spent, he likes to spend so much time in chapter 2 on resonance because we see it all the time, okay? And I hope by now you're like super comfortable with resonance and you don't have any issues drawing structures out. So the first step is the nucleophile attacking the electrophile. Once the electrophile is on there, you get these resonance structures, which means delocalization, stability, whatnot. Then comes in the conjugate base and then picks up the proton. Now, where is the conjugate base coming from? Where is the electrophile? That's the whole thing, right? Like I'm just writing things in a very generic manner right now. But our point is going to be, as we go through these reactions, is learn what the electrophile is, what the conjugate base is, and so on and so forth, okay, as we go on. I'll explain all of those to you as we go on. So here are the reactions we are going to cover in aromatic reactions. There are a whole bunch, and they're all very interesting reactions, okay? So 1, 2, 3, 4, 5. You're going to have 5 prongs coming out. We do a lot of prongs in organic too because there are so many reactions, okay? So 1, 2, 3, 4, and 5. I'm just going to use my whole page for this. You don't have to. Okay, so the first one is going to be halogenation. That's the reaction I was writing with the bromine. So we'll talk about this. This is called halogenation. The next one is nitration. So HNO3, H2SO4. Put a nitro group on here. I told you yesterday we were going to make all these names that we have learned in nomenclature. So here are some of them now. Not nitrobenzene, nitration. Some of these groups, we have not really learned before, like nitro group, right? This is the first time you're seeing a nitro group. But anyhow, just a side thing here. And this group also, SO3, H2SO4. So this is sulfonation. This is called sulfonation. If you hear voices, that's because somebody's in the house. Hopefully you can focus on mine. Sulfonation also you've not seen before. It's the first time we are doing it and possibly the last time. The other time we see sulfonation is actually in alcohols, because when we use sulfuric acid, that is also sort of sulfonation. Okay, the next two reactions are a little bit different. This is called Friedel-Crafts alkylation. And the next one are COCl. This is specific Cl, okay? The top one I wrote as X. Let me change that to Cl as well, actually. That would be good if I change it to Cl. That way you don't get, you don't use any other halide. AlCl3 and okay, Friedel-Crafts acylation. I hope you wrote all of them down. I'll give you another minute to write everything if you are writing everything. Okay, if you didn't write everything, it's okay. We'll catch up because we're going to have to write these reactions again. Okay. All right, let me go over all of these first of all, okay, with you one by one, and then we'll take them one individually as well, okay, with the specific reaction. So the first one is halogenation. Halogenation, you put a halogen on the benzene ring. Now remember, the halogens we've always talked about is chlorine and bromine, okay? So one thing I want to mention here to you, I wrote X2. X2 is, X is just halogen in organic chemistry. Whatever halogen you're using, that is the iron compound you're using. So if you're using Cl2, then you have to use FeCl3. If you're using Br2, then you're going to use FeBr3. You're not going to mix and match these compounds, okay? Whatever I have written on the top is the reagent. Whatever I've written on the bottom is the catalyst, okay? That is how I differentiate my things. However, you're most welcome to write like this also. And you will see me also writing like this. If I have more than one step for a reaction, I will write as comma, like one of this, and then two, I'll write something else or whatever. Okay, so I mean, you can write either way. Right now, I'm writing it like this so that you can remember what the catalyst is. Okay, all right. So X2 and then FeX3, that's the catalyst here. The halogenation that you do here is usually going to be for chlorine and for bromine. We don't do fluorination this way. And for iodine, you need a different kind of catalyst. Okay, you don't need this catalyst. So you might see it somewhere. So anyhow, that's halogenation. The next one is nitration, which is nitric acid and sulfuric acid. Now, again, remember I told you if we don't write anything before these acids, it means they are concentrated acids. Okay, so both of the acids here are concentrated acids. So that's nitration. Now here, HNO3 is the reagent and H2SO4 is the catalyst. Okay, that's how it's working. Then the next one is sulfonation. Sulfonation is SO3 and then H2SO4. The next two reactions that we have, okay, these two reactions, these are really very interesting reactions. We're going to spend some time on these when we get there. So Friedel-Crafts alkylation and Friedel-Crafts acylation. Because I want to remind you of one thing and I want to point it out to you that this is a carbon-carbon bond formation as well. Okay, because our group is an alkyl group. So you're adding an alkyl group here. So it's a carbon-carbon bond formation. And so is the acylation. Okay, in the acylation, you're adding a keto group also in there. So the catalyst we use for Friedel-Crafts is usually AlCl3. Now, one of the things that I would like you to do, if possible, okay, is when you remember these reagents, you remember the catalysts that go with them, okay? You don't want to use any other catalyst. So for example, for sulfonation and for nitration, you're always going to use sulfuric acid. You're not going to use aluminum chloride, okay, for that. Now, sometimes what Klein does is Klein will tend to use aluminum chloride here. You know, when he's doing chlorination, he uses aluminum chloride, and that's okay. So long it's chlorine and chlorine, it's fine. Okay, but wherever you have H2SO4, you cannot switch that out. Okay, you have to use sulfuric acid in those cases. So here also for Friedelkraft, you cannot switch out the catalyst. Okay, you have to leave it as aluminum chloride. All right, so no mixing and matching and no moving things around. Okay, so that's the introduction. Now what we are going to do, and by the way, if you notice this, these are all mono substitutions. Okay, which means I'm substituting only one hydrogen. My goal now is to go through all of these reactions one by one, explain to you what the electrophile is, because all of these are just generic reactions. Okay, so now we're going to learn about what the electrophile is that is generated, and the conjugate base and whatnot. So that's what we're going to do. I want you to note one more thing before I move on from here. If you look at the catalyst, look at all the catalysts here. This one, this one, this one, and aluminum chloride. If you look at all these catalysts, these are all acids. Whether they are Lewis acids or the general sulfuric acid, they are all acids. So FeCl3, iron 3 chloride, that's a Lewis acid. Aluminum chloride is also Lewis acid. So that's an important thing, okay, because that's what's going to help us to generate the electrophile. That's the important thing here. So let's start with the first one, which is halogenation. And once you see one of them, everything is the same. And by the way, I don't do the mechanism anymore because the mechanism for all the reactions is the same, which I wrote over here for you. Okay, so here, let me give it the title. So you see it, in the notes. So here, this is the mechanism of the reaction. So once you generate the electrophile, I will not be writing all the resonance structures out and all that kind of stuff. Okay, so I'll just go from one to the next and then to the final. That's it. That's what I generally do. So let's start with halogenation. So you start the reaction actually with bromine. You don't start with the nucleophile. Our first job is to generate the electrophile. So here then you're treating this with FeBr3, which is the catalyst. Now here the bromine is going to give its electrons to iron, because iron is the Lewis acid. So it's accepting that lone pair of electrons. So you end up forming Br, and then Fe. And the 3 Brs are still there. Now you can write it any way you want to. I'm just going to write it like this. You can write FeBr3 if you want, okay, on there. That's totally fine. You might remember from long time ago when we were doing chapter 3, acids and bases, we wrote out some Lewis acid-base reactions. And those Lewis acid-based reactions, they don't give you any water or anything like that, right? So you will just have the positive and the negative. So here you have the bromine giving electrons to the iron, so which means bromine is going to be positive. Iron is accepting electrons, so it becomes negative. So then the next step is, we haven't formed the electrophile yet. The next step is actually to form the electrophile, which is like this. Okay, so you break this bond. And so now in this case, you generate the Br plus. That's your electrophile. And then you also have, I don't know why that's colored that way. I think I forgot to change my ink color. And you also have this. Now, this is the conjugate base, okay, that we've been talking about. And then this is the electrophile. So you generate these two. Now comes in the benzene. And picks up that bromonium. I don't know what to call it. because Br plus, like we've never seen Br plus before in our life, you know. We see bromide, and I've showed you bromonium ions before, but Br plus as an electrophile, we've never seen that before. That's why I said aromatic chemistry is very different. So then here, I'm just going to draw the hybrid. Okay, so here you have the electrophile, and here is the hydrogen, and here is the other hydrogen. And then the last step is where FeBr4 minus will come in, and this will now pick up this hydrogen. You don't even have to write the second hydrogen if you don't want to, because that's really not doing anything. And then you also get HBr in the process. And remember, one of the things about catalyst is that catalysts are regenerated at the end of the reaction. So you don't have to write all of that out. I'm just writing it to show you that HBr is formed as a result, and FeBr3 is regenerated as a catalyst. But then, of course, here is our product. So this is the whole mechanism. Now, if you're wondering, okay, let me give a minute to you to finish writing all of this. Okay, so hopefully you've written everything down. So in case you're wondering, like, what should I know from this one? Do I need to know the whole mechanism? What generally is asked of you in exams, what I will ask you, and, you know, I mean, you're lucky because we're not on campus. You'll be taking the ACS exam if we were on campus. Right now, you'll just take my exam. But in those exams also, you will be asked how the electrophile is generated, okay? So, which means that the first part of it, that's the important part, because you need to know how this is formed and then how this is formed. Okay, that's the important thing here. So these are the things. Now, regarding this intermediate over here with the nucleophile attacking and all that, sometimes you're asked about the resonance structures, okay, which I hope you can draw the resonance structures already. So that's sometimes what you're asked, okay? But other than that, everything else is normal. And after a while, what happens is, hold on one second. It's telling me my computer is running low on battery, which is really weird because I thought it was all connected. Give me a second. Anyhow, okay, so that's halogenation. Any question? Any question on this? All right. So make sure that you keep your catalysts together. Okay. So for bromine, you will use FeBr3. For chlorination, you can use AlCl3. Or you can use FeCl3 also. Okay, those are fine. So that was halogenation. Now let's talk about nitration. And again, the main thing is, how is the electrophile formed? So let's do that. Nitration. So HO and then NO2. So that's HNO3, right? So HNO3 is the acid. So I'm writing it in a little bit different way. H2SO4. H2SO4 is stronger than nitric acid. Okay, and that's why we're using sulfuric acid as a catalyst. So here, this is what happens. HNO2. So the OH of the nitric acid is getting protonated now, which is really weird, right? You never think of nitric acid being base, okay, and picking up a proton, but because sulfuric acid is stronger than nitric acid, it's picking up a proton. 1 second. Okay, so once you've generated that, now we just need to generate the electrophile, which is this, that the water goes away. So minus H2O, and then you have what is called the nitronium ion, or nitroso. I don't know what it's called. There. Now, not very much going on. You have the benzene coming in there. That, and that's it. The hydrogen will be picked up by the water. I'm not even going there anymore because really, you will not be needing that so much. So the main thing here is going to be, again, how you generate the electrophile. Okay, that's the important thing here. Questions? Moving on. Sulfonation then. Sulfonation is interesting because of a couple reasons. Okay, so number one, it's all in equilibrium. That's one interesting thing about this, because usually we don't do reactions in equilibrium, right? So then here is the sulfur trioxide. So the sulfuric acid here, okay, you saw that I wrote up there because I wrote SO3 and then H2SO4. I wrote this. Now, sulfur trioxide is a gas, actually. And what happens is that you don't really get sulfur trioxide. What you end up getting is sulfur trioxide mixed with sulfuric acid, and this is called fuming sulfuric acid. So the fuming sulfuric acid has excess of sulfur trioxide in it. So usually sulfuric acid would be like 17 molar concentration, but fuming sulfuric acid is like 22 molar. Okay, so it's got a lot of sulfur trioxide in it. And literally when you open the bottle up, it will start fuming, okay, in there. So it's very, 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 very dangerous to work with. In any case, so that's kind of what happens. So the sulfuric acid is there. It's not doing anything though. Okay, so the sulfur trioxide is good enough. And this is kind of what happens is the benzene will then attack the sulfur. And here is what you form, SOO minus. That's the sulfonate, and then comes in the water. There's always going to be water when you have acids. And so then the last step is going to be the protonation of the oxygen. So the sulfonation here, it's an equilibrium. What this means is that if you add sulfur trioxide, you go forward. If you add water, you'll go backward. So you can remove the sulfur group, the sulfonation also, okay, from there. So it depends what you want to do. So like, why would you want that? Okay, and this is the interesting thing about the sulfonate group. The sulfonate group really has no synthetic use, okay, which is why we never talked about it before. It has no synthetic use. The only thing it does for a benzene ring is it provides it polarity. Benzene ring by itself is a hydrocarbon, C6H6. It's a very non-polar substance. So when you add a sulfonyl group to benzene ring, it changes its property to being a little bit more, having a dipole moment. Now, the sulfonate group is not really useful for any other reason except to create that dipole moment. And that is used a lot in medications. Okay, so let me explain to you what that means. When we were talking about the skin a long time ago, that the skin is a bilipid layer. So you have this, right, as your skin. And the cell membrane also, right? The cell also is, a bilipid membrane in there. So this is the polar head. And then here, the tails that I have drawn here, that's the lipid layer. In that lipid layer resides all kinds of things like, proteins and enzymes and whatnot. When any of us take any kind of medication, that medication has to get inside the cell. To get inside the cell, it has to cross this barrier, okay? So now water is the most common solvent. Our body is also made up of water, 70%. So we need the drug to be able to go into the body using the water, but then it also has to be non-polar enough to cross this barrier. And then once it gets inside the cell, then there is water again. So like we have this big issue of polar, non-polar all the time, okay, in the body. And then when the body excretes things, it also excretes it as water. So lots of issues here. And so what the sulfonate group does is it provides the water solubility. Okay, so as I mentioned to you before, a lot of the medicines that we take, they actually have benzene rings in them, which makes it non-polar. So if it's non-polar, it can get through the membrane, but how will it get to the cell? So the transportation issue here. So in order to induce a little bit more polarity into the molecule, you add a sulfonyl group. Okay, so the sulfonyl group generally is not doing a whole lot there. Okay, it should not change the nature of the benzene ring except for polarity. Okay, so the binding and all that, it doesn't help. And because it is reversible, sometimes the sulfonyl group will actually fall off, okay, in the body. So then it can just be excreted, okay, using water. But that's the reason why sulfonations are done. The other reason we do sulfonation is also to do some targeted synthesis, okay? And Klein has done that a lot. I don't do a whole lot of targeted synthesis in our class, but I'll see if I have time, I'll do it. Okay, and I'll show you how we use sulfonation for that. Other than that, sulfonation is really not synthetically useful, okay, as a functional group. Okay, so then after that, now we have our two main reactions, which we really need to spend time on, and those are the Friedel-Crafts reactions. So there are two reactions, Friedel-Crafts alkylation and acylation. So I'm going to take the first one, alkylation first. Friedel-Crafts, two scientists, they got Nobel Prize for this reaction because carbon-carbon bond formation, right? Diels-Alder, Grignard, all of these, any kind of carbon-carbon bond formations, they're always going to be challenging. So this is another one of those, and especially getting it on a benzene ring, So again, remember the challenge is getting one carbon to be positive and one carbon to be negative. So the nucleophile here is obviously the benzene ring. So let's see how to do this one. So we'll take ethyl chloride, treat that with aluminum chloride, which is our catalyst. The reaction starts the same way as it did for chlorination. Let me just take you up there for a second. So chlorination, bromination, that's how the reaction started, is the halide attack the Lewis acid. Okay, and once that happened, then you have the breakage to give you the cation. That's what we are going to do here also. So chlorine attacks the aluminum. So then you get CH3, CH2, Cl, and that is bonded now to AlCl3. So if you want to draw bonds, you're most welcome to. That helps a little bit. So plus here, and remember aluminum is receiving the electrons. So that is negative. And then you break the bond right here. And you get the ethyl cation and the aluminum chloride conjugate base. So here is an issue, which I know you'd like to forget, but we can't forget, is that this is a carbocation. And carbocations with them bring all sorts of issues like rearrangements. Okay, so we'll talk about that a little bit later. Now comes in the benzene right here. Okay, look, my arrow is so pretty. Okay, I'm gonna redraw that. There, it's prettier. So then there's the CH2, CH3, there is the hydrogen, and then comes in the aluminum chloride minus, picks up this hydrogen, and all is good. Okay, so hopefully everybody's written this by now. This reaction works really well, okay? Aluminum chloride is nasty to work with, but other than that, the reaction works really well. We do this in our lab, not this alkylation, we do acylations, but it works well. So the main thing again is the generation of the electrophile. The electrophile here is going to be the carbocation, and all the problems that come with carbocation we have to deal with, but that's okay. And then the nucleophile comes in, attacks the carbocation, and then we're all set, okay, from there on. So then you get your alkyl benzene, okay, all very nice, no problems at all, okay? So things that we learned about the carbocations, you have to kind of remember, okay, because the carbocation is generated over here. First of all, you can do reactions with this, like the ethyl chloride, which really, if you look at this carbocation, it's actually a primary carbocation. And primary carbocations are not all that stable, okay? So it's possible that in the solution, it's not really existing by itself, but it is in existence with the aluminum chloride. So it's kind of paired up together, okay? But otherwise, you know that primary carbocations are not stable. The same thing goes for methyl carbocations. Okay, these are not going to be stable as well. So, but you can do reactions with them. It's very common to do this reaction. So you take benzene, treat that with CH3Cl and AlCl3. You're going to do this reaction a lot, you know, and this is how you make toluene, right? So you add CH3 to a benzene ring to make toluene. Not that you may need to make toluene, but still, this is how you would do it. So you can do the reaction, which means it is possible to do this reaction regardless of the fact that a methyl cation is not a stable cation. But the thing is, you're not isolating anything and all the ions are in the solution, so they will stabilize. Okay, one way or another, they will stabilize. But if you have a larger compound, then we'll have issues. So first, let me ask you if there's any questions on this one so far. Okay, so let's do another reaction on Friedel-Crafts. And this is where you have something like this, okay? So now in this case, you're thinking, okay, yeah, fine, you know, this is possible, and I'll go ahead and do this. Remember, the carbon that has the chlorine is the carbon that will join, okay, with the benzene ring. Okay, so this is what you're thinking, but you don't form this. You end up forming this. So, which means that there was some rearrangement going on. So let's see what was going on here. Okay, so now if you look at the alkyl halide, the aluminum chloride, the carbocation that you're going to generate is going to look like this. But carbocations will rearrange. We know that also. So there is a hydride shift, and then you end up getting an isopropyl cation. That isopropyl cation now will react with the benzene. Okay, so the propyl cation actually never reacts with the benzene, and then you end up getting isopropyl benzene. So you have to be careful when you do these reactions, okay, with the Friedel-Crafts, because rearrangement is always possible. I hope you are the class that's going to make me proud and not forget the rearrangements. Okay, because this is something that everybody forgets. Every class, I've been waiting for a perfect class where nobody forgets rearrangements. Okay, so let's hope you are the one. Okay, because every time you take a long chain carbon, there will be rearrangements because primary carbocations are not stable at all. Now, if you were to take a secondary halide, this is not a problem, right? So this will react and give you isopropyl, no problems, okay? But for any other thing, you kind of have to be a little careful, okay, with what kind of product you're going to get, okay? So that's Friedel-Crafts alkylation. You can also use alkenes. So for example, if you don't have an alkyl halide, you can also use this. Again, you have to use the catalyst. So here, because this is a double bond, now you can change your catalyst. So you can use this or this. So you can't use sulfuric acid with aluminum with alkyl halide. Okay, but with an alkene you can, because the goal is just to generate a carbocation at this point. With the alkyl halide, you need to have aluminum chloride. Remember that. So the product is still going to be isopropyl here. Wherever the double bond is, that's where you will get the connection. Okay. So this is alkylation. We'll do acylation and then we'll take a little break. Okay. So for Friedel-Crafts acylation, the way you start is you start with an acyl chloride. So this is an acyl group. Acyl group does not mean any number of carbons, any specific number of carbons, I should say. Okay, because acyl is just like an alkyl group. Okay, so which means it's not specifying that you have one carbon or two carbons. It's just saying it has, you know, a number of carbons, but you have a carbonyl on there. So now when you treat this with aluminum chloride, chlorine again will react. So CH3, CO, Cl, and then aluminum chloride. I'm writing everything out so that you have it for your record also. And you need to know how the electrophile is generated. Okay, so there now, this is broken. CH3, C double bond O, and now here is the positive. And you have the AlCl4 as well. In comes the benzene. I'll just write the final product. You will always form a ketone in this, always. This is acetophenone, as you'll remember from your nomenclature. So acetophenone, you know, is methyl phenyl ketone, right? So you need only one methyl group there. That's very specifically acetophenone. The acid group, if you remember from long time ago, from mercury acetate, I told you the acid group was CH3CO. That is the acid group. So that's why it's called acetophenone. Okay, so in this one, you can see that our electrophile is right here. And the good thing about this electrophile is there is no rearrangement. And the only reason I'm mentioning the rearrangement is because the Friedel-Crafts alkylation did the rearrangement. Acylation cannot do rearrangement. All the others, chlorination, nitration, sulfonation, no rearrangement there. It was a very small electrophile. But now we're getting into carbon electrophile, so it's a little bit different. So here you don't have any rearrangement. You get a nice clean product. That's why we do this reaction in our lab. And I think you might be doing it in yours as well. You can take any long chain here without any problem. Okay, so for example, here, I can take any long chain acyl chloride with aluminum chloride. Don't forget the catalyst, okay? Please don't forget the catalyst, because without catalyst, this reaction is a no reaction. So 1, 2, 3, 4. And on carbon number 1, there is a ketone. Okay, so 1, 2, 3, 4. All right, so this is acylation. There is still lots to talk about Friedel-Crafts alkylation and acylation, more so for acylation than alkylation. For alkylation, the main thing was the rearrangement. Okay, that happens over here. So I don't think I wrote it, but I'll write it here somewhere. I think in this one, right? So rearrangement, that way you will not forget. Possible because of carbocation. Okay, so let's go ahead and take a little break right now. I think I need a little water myself. So it's 11, almost 10. So let's come back at 11:15 and we'll make sure we finish at least all the mono substitutions today. Okay, so let's do that. So many new reactions, but then these two, the Friedel-Crafts acylation and alkylation, new carbon-carbon bond formations. Okay, so as I said, the advantage of doing acylation is that there are no rearrangements in here and you get your chain on there without any problems, except of course you're getting a keto group there too, right? So that's an issue. You're not getting an alkyl chain, you're getting a ketone group and then the alkyl chain. Okay, so few things to talk about here. First of all, the acyl chloride itself, okay, because I haven't talked about that at all. So acyl chlorides are RCOCl. And acyl chlorides are really interesting in the sense that they're very reactive compounds. These are acyl chloride. So these are reactive compounds and they're part of the family of carboxylic acids. Okay, so when we learned functional groups last semester, I taught you the 2 oxygen groups, right? So the carboxylic acids, carboxylic esters, okay? And there was another one, amide, which had only 1 oxygen, but it still had the carbonyl in there too. Carboxylic acid, carboxylic ester, carboxylic amide. Actually, it's not carboxylic amide, it's amide. So these 3 functional groups, they actually belong to the same family. And by family means that they behave the same way. You know, that's what families do. So here, the acyl chloride is also part of that family. Now, we didn't mention it back in the functional groups because acyl chlorides don't occur naturally. Okay, so the other 3 esters, acids, and amides, they occur naturally, but not the acyl chlorides. They're very reactive, so you generate them only in the lab and then you use them up. Okay, so how do you generate them? Okay, for the acyl chlorides, you take any acyl chloride, carboxylic acid, treat that with thionyl chloride or PCl5 or PCl3. You remember these 3 reagents we've dealt with before. And the way you saw them before was when we took an alcohol and treated them with thionyl chloride, okay, in order to get the chloride on there without any rearrangement. So you can take any acyl, you can make any acyl chloride from the corresponding carboxylic acid. It's a very common way of making acyl chlorides. So for example, you can take acetic acid, treat that with PCl5, and then make CH3COCl. It's up to you how you want to write your oxygen. You want to write the double bond, or you just want to write it in a line. It's up to you, okay? But you have to be able to recognize it, okay? That's for sure. Acetic acid will give you acetyl chloride. This is acetic acid. Acet, okay, acet. Remember acet, okay, is the CH3CO, that is the acet, okay? So acetic acid and then the acetyl chloride, that's how it's formed. So this is how you form the acyl chloride. Another thing that works for doing Friedelkraft, so acyl chlorides, you can get them from the store also, by the way, okay? So unless you want to make a specific acyl chloride, and if you're open to any acyl chloride, get them from the store, okay? No worries about that. But here is how you make them. And the reason I'm telling you how to make them is because sometimes I give that as part of your reaction, okay? How do I give that? This is how I will give it to you. So here is an acid, and then I will say, okay, you know, you treat this with thionyl chloride. What do you get? And then you treat that with benzene and AlCl3. And then what do you get? Okay, so this could be a sequence of reactions. So then in this case, you will fill in all the blanks, and your blank would be then, okay, so I will get acyl chloride here, and that acyl chloride can now react with benzene. And 1, 2, 3, 4 carbons, and then that. So you can see that, you know, we write reactions quite differently, okay, for benzene reactions, because we are so used to seeing substrates and products and things like that. But here things are written just a little bit different, you know, and we have to get used to everything. You can also use anhydrides for these things. So let me introduce anhydrides to you. Anhydrides are also part of the carboxylic acid family. So RCOOCOR, and you're probably thinking, oh my Lord, so many oxygens. Yes, so many oxygens. So carboxylic acid themselves have, you know, 2 oxygens, and now you're adding 1 more oxygen to that. So this is not a per acid, okay? It's not a per acid because you got the 2 carbonyls in there, okay? Per acid has only 1 carbonyl in there. So how does this work? Well, exactly the same way as an acyl chloride would. So let's say you have CH3, CO, O, CO, CH3, AlCl3. Your catalyst is the same. That hasn't changed. And your product is still acetophenone plus, I'm just writing it like this so you can keep the, you know, frame of mind, okay? The correct frame of mind here. That's the leaving group. But the leaving group can also be on the left side. Doesn't matter because this is a symmetrical anhydride. It doesn't really matter, okay, which side is the leaving group. So you can use anhydrides, you can use acyl chlorides to give you the ketone, okay, or the acylation. Now, the leaving group, you don't really have to show. Remember that, okay? You don't have to write the leaving groups for me. The main thing is the product, always. Because when you're doing synthesis for me, remember, you never show me the leaving groups, okay? And you don't even have to show me mechanisms. Some of you do. You don't have to at all. For synthesis, you don't have to. Okay, so this is all fantastic. Okay, this is all great that we have learned about acylation and alkylation, but there are some issues. Okay, so now we need to talk about those issues. Some of these you will understand, and some of these you may not. And you may learn them later. So you just need to memorize them right now. So the drawback of Friedel-Crafts. This one, the first one, generally we don't follow, even though it is a drawback, but we never follow it in the sense that for alkylation, multiple alkylations can happen. I don't even know what I'm writing anymore. So everything was merging into one another, multiple there. Can occur, which means that, you adding one alkyl group and then another one adds and another one adds. So that kind of thing can happen, but if you stop it at a proper point, you can probably still get some good product. Okay, so or maybe just don't do this reaction then. Do it another way. Don't do alkylation, but we do alkylation. That's what I'm saying. This is a drawback, but theoretically we are going to follow. Okay, theoretically we are still going to do alkylation. You're going to have to do that, okay, as part of your synthetic steps. Number 2, you already know, rearrangement. Occurs in Friedel-Crafts alkylations. And the rearrangement, remember your rules for rearrangement. You have to form a more stable carbocation. If you're not forming a more stable carbocation, then no more. You don't have to do rearrangements, okay? So don't give me primary carbocations, but if it's a secondary, it's fine. But if the secondary can go to a tertiary, form the tertiary carbocation and then do the reaction, okay? So you always have to pay a little bit attention for alkylation. Number 3. Both of these, Friedel-Crafts, alkylation and acylation, don't work if there are electron withdrawing groups on benzene. What are electron withdrawing groups? Oh my God, you have the list for all of that. Nitro group, carboxylic group, carboxylic ester, amide, nitrile. You have the list from Diels-Alder reactions. Bring that list out now, okay? So use that again. I told you to write that on an index card or a separate page or something. You're going to use that list again because all the electron withdrawing groups that make a good dienophile are the same electron withdrawing groups here also. Okay, so both the alkylation and acylation do not work if you have electron withdrawing groups on the benzene. I tell you, the ones that you forget most are these 2 rules. Multiple alkylations, I'm telling you to forget that anyway. So you're not even going to remember that one. But the ones that I do want you to remember, you don't remember those. So let's see, we'll make this one a perfect class. Okay, we will remember all these things. So they don't work if there are electron withdrawing groups A, B, if there is NH2 group on benzene ring. NH2 meaning aniline, right? NH2 on a benzene ring is aniline. So aniline will not do Friedel-Crafts alkylation or acylation. This is what I call a chocolate question. And the chocolate question is why? This one you should know the answer for. So I'm going to let you think about it. You don't have to answer that today for me. If I remember, I'll ask you tomorrow. So if there's an amino group on benzene ring, why does it not work? Okay, the electron withdrawing, I'm going to cover that. Okay, I will be going over that at some point. Well, maybe tomorrow. But the amine group, why that does not work, you should be able to answer that one. So I'm going to leave that for you. Okay, it's to think about. So these are the drawbacks, unless you want to tell me right now. It's kind of challenging, okay, to think about right now because there's so much information at this time also. Okay, so these are the drawbacks. That's it, just 3 drawbacks. Okay, but they are big drawbacks because when you're doing a synthesis, then you want to make sure you do things in the proper sequence. So you don't run into anything in which I have to write then, oh, this reaction is not going to take place. Okay, so it happens a lot. Okay, because right now we're doing mono substitution, right? Because mono substitution is just removing one hydrogen, replacing one hydrogen. But where we are going with all of this is going to be the di substitutions, okay, where you have 2 substitutions on there. So if you have 2 substitutions, well, then which one do you put first? Which one do you put second, right? That becomes really important. So that's where the challenge is going to be for you to remember some of these things. The rearrangement can happen even if you have mono substitution. It doesn't matter, So that's something you have to take care of. Okay, so one of the questions that should still remain with us is this one. Okay, so remember this reaction that I wrote down. And the only reason I'm bringing this up is because, of course, we have a solution for this. And I said to you that this one will not form because it will undergo rearrangement and give you this. Because the propyl cation is a primary carbocation, which will then rearrange to give you an isopropyl carbocation. So we talked about this already, okay? So the thing is, what if I want to make propyl benzene? I don't want to make isopropyl benzene. I don't care for isopropyl benzene. I want propyl benzene. How do I make it? So the way to make it is actually a 2-step thing, not a 1-step thing. So here's what you do. You take benzene and you do Friedel-Crafts acylation on that. I'm going to take 3 carbons. And here it is. Acyl chloride, 3 carbons, 1, 2, 3, because I want to make propyl benzene. AlCl3. You're going to get so tired of drawing benzene. And now you get this. And you're thinking, fine, this is still not propyl benzene. Well, you can reduce this now. So if you reduce the keto group, then you can get propyl benzene. So it's a 2-step process, but it's doable. What is the hydrogen here? The active hydrogen here, the reducing agent here. There are 2 that you have a choice of working with. One is called Clemmensen reduction. Which uses zinc and mercury in presence of hydrochloric acid. You don't have to remember Clemmensen, although, I mean, I do mention the name all the time, so hopefully you will correlate the Clemmensen with zinc and mercury. The other one is Wolff-Kishner reduction. So both these reductions, and this one has NH2, NH2, and this is in presence of sodium hydroxide. So now you have a basic condition and you have an acidic condition. This is called hydrazine. Now you can do any kind of reaction, or I should say you can make any long chain alkyl group straight chain on benzene, because all you have to do is you have to do acylation first and then reduce it in order to get your alkyl chain. Now the reduction here, Clemmensen reduction and Wolff-Kishner reduction, please remember, these are the only two you can use. You cannot use LAH, because if you use LAH, you will get alcohol. Okay, so you can't use those. You have to use the ones that I'm giving to you, because this is for ketone. Okay, so we haven't done ketone chemistry yet. That's going to be the next chapter that we do. So you haven't done ketone chemistry yet. So you don't know these reagents yet. Okay, they're coming up again. But now you know, okay, they're coming up again next week, okay, when we do aldehydes and ketones. So this is the reduction that you can do in order to make the straight chains on benzene rings then, okay? So there is a workaround. There is a workaround to making straight chains. And this is something that we tend to forget. Okay, one more synthesis. And this is called the Gattermann-Koch synthesis. So this synthesis, let me show you what, let me write the reactants and products first. So you can see the resemblance, okay, of what I'm trying to do here. I want you to look at the Friedel-Crafts acylation that I have on the top. So I have the acyl chloride and aluminum chloride, and that's giving me a ketone, right? A ketone is an internal functional group. It is surrounded by carbons. Aldehyde is a terminal functional group. It has one carbon and one hydrogen. It can have two hydrogens also, okay? So, but in this case, there is the benzene ring on one side because, of course, we are on aromatic compounds. Okay, so what is it that I want you to do here? I would like you to take 30 seconds, probably should not take you long, and write the reagent that you will need here. Okay, so look at the Friedel-Crafts acylation that we have. Look at the reagent we are using there, and then write the reagent for the Gattermann-Koch synthesis. Okay, I will not ask you to write here, so feel free to write whatever you want, and then I'll give you the answer, okay, in 30 seconds or so. Hopefully you wrote something, and hopefully you definitely wrote the aluminum chloride, because without the catalyst, nothing is possible. So that is for sure, that should be there. And then hopefully you're looking at what is here and what is here, and look at what is here, because that's the group that is attached. So you will have this, and then you have the chloride. Hopefully you have this. I'm not looking at your notes. You are looking at your notes. And if you have this, you can give yourself a little pat on the back that you got this correct. The only thing is that this does not exist. So which means we put it in square brackets. So if you wrote it, it is still correct. It does not exist does not mean that you can't make it. You can make it, but it just has to be generated in C2, okay? So the Gattermann-Koch synthesis is actually carbon monoxide and HCl and aluminum chloride. These two, when they combine, will generate this intermediate. And that is how you get the aldehyde group on the benzene ring. Okay, so you still need the catalyst. And this is, of course, benzaldehyde. So we've made a lot of our aromatic compounds. Okay, today we made chlorobenzene, toluene, acetophenone, nitrobenzene, and now benzaldehyde. Good. Any questions? Anything that's bothering you right now? Okay. So let me take you back to our chart for the mono substitutions that I wrote. Oh my gosh, it was so long ago. This one. So we've finished all the mono substitutions now, by the way. Okay, this is it for mono substitutions. Now we're going to go to something else. So in the mono substitutions, these are the reactions. The fun thing about benzene reactions is that even when we do di substitutions, we'll be using the same reactions again. Okay, so which means you have to learn these reactions one way or another. Okay, so all the reagents and the catalysts that go with those reagents, you still have to learn them. You can add to this chart if you want to, okay, because now that you've learned the Gattram and Koch synthesis, you've learned the reduction. So you can add on to this chart a little bit to help you with remembering all of these reagents. Okay, so what I would like to do, I think at this point, is I would like to stop right now, because the next part, the di substitutions, I think I'm going to do next week, because the di substitution is a little bit more detailed, okay, for us to start today and even finish tomorrow. I can't do it, okay, it's a little bit long. So tomorrow, since you have an exam also, I'm going to try and limit myself in such a way that you're able to do this, which really, honestly speaking, there is not a whole lot in this. Okay, I know it took me more than an hour to do this, but that's only because I was going through all the mechanisms and everything, okay, in which I don't ask you the mechanism. I ask you for some resonance structures in the multiple choice questions, but otherwise the reagents are really the main thing here. And the other thing is what I've highlighted, which is the generation of the electrophile. Okay, that's the main thing. So go over that at some point, today, after you finished your aromaticity homework. But other than that, in the mono substitution, there's really not all that exciting. Okay, so let me show you what I mean by exciting, because, I mean, you have to have something to go with it. And so the self-study that I have there for you for aromatic reactions, if you open that up, I don't remember what page it is, but here, I mean, mono substitution, there's only like one page. That's it. And you may want to do this. Okay, definitely do this today. Okay, so mono substitution, you just have all the reactions that are something that we covered. So you just write them out and that's it. And after that, it's really all about di substitutions. Okay, and so you can't do that yet. Okay, and so in this case, just go ahead and do the mono substitutions and write all the reagents, learn all your reagents. That's the important thing. So what I want to do is, I think I want to stop here so you get to practice those reactions on your own. You can do that and do your homework. You have a quiz also due today for aromaticity and whatnot. Tomorrow when we come back, again, I don't want to keep you too long tomorrow. So we will have a short portion in which we are going to do some side reactions, okay? And the side reactions, one we have already done, okay? Whether you realized it or not, because it was a side reaction. The reduction is a side reaction, which means not on the benzene ring. It's outside the benzene ring, okay? That's called a side reaction. So we will do the side reactions tomorrow. There are only like 3 or 4 of those reactions, okay? So we'll do some of that, and that then should be on the exam, okay? Does that feel okay with everybody? Yep. Okay. All right. So a lot of stuff today for you to absorb and have fun absorbing everything, I guess, so.